Imagine for a moment that you hold a coin in your hand. Not just any coin, but a very special one. Its twin, its partner, exists on the other side of the universe, billions of light years away. Now you flip your coin and it lands on heads. At that exact instant, without any delay, without any signal traveling through space, without any wave or particle or force connecting them, the other coin becomes tails. Not a millisecond later, not after light could travel between them. Instantly, simultaneously, as if distance itself does not exist between these two objects. This is not science fiction. This is not a thought experiment from a philosophy class. This is quantum entanglement. And it is one of the most experimentally verified phenomena in all of modern physics. Scientists have tested it across laboratories, across cities, across continents, and even from Earth to orbiting satellites. Every single time, the result is the same. Two entangled particles respond to each other as if they are one single entity, regardless of the distance separating them. But here is where things get truly strange. Here is where the mystery deepens into something that has haunted physicists for nearly a century. Despite this instant connection, despite this seemingly magical link that laughs at the speed of light, you cannot use quantum entanglement to send a message. You cannot use it to transmit even a single bit of information faster than light. The connection is real. The correlation is real. The instant response is real. But communication through it is impossible. Not difficult. Not beyond our current technology. Fundamentally, absolutely, mathematically impossible. Why? Why would the universe create such an incredible connection and then refuse to let us use it for communication? Why would nature build a bridge across the cosmos and then forbid anyone from crossing it with a message? This is one of the deepest questions in all of physics, and today we are going to explore it from every possible angle. We are going to start from the very foundations of quantum mechanics, build our understanding piece by piece, explore the great debates between the greatest minds in history, and arrive at an answer that is as beautiful as it is frustrating. By the end of this journey, you will understand something that confused Albert Einstein for the last 3 decades of his life. You will understand why the universe has this strange rule built into its very fabric. And you might just come away with a completely new understanding of what reality actually is at its most fundamental level. Before we dive in, I want you to do something. Think about what you believe entanglement is right now. What is your current understanding? Drop it in the comments below. Because I promise you, by the end of this video, your understanding will have transformed completely. And if you love deep explorations of the universe's greatest mysteries, hit that subscribe button right now, because this channel is dedicated to taking you on exactly these kinds of journeys. Now, let us begin. To understand why quantum entanglement cannot send information, we first need to understand the world it comes from. The quantum world. And the quantum world is nothing like the world you experience every day. When you throw a ball, you can predict exactly where it will land. When you open a box, the object inside was always there, in a definite state, waiting to be seen. When you measure the temperature of water, the water had that temperature before you measured it. These seem like obvious statements. Common sense. But at the quantum level, every single one of these intuitions is wrong. The quantum world operates by completely different rules. At the scale of atoms and subatomic particles, objects do not have definite properties until they are measured. A particle does not exist in one place. It exists in a cloud of possibilities, spread out across multiple locations simultaneously. It is not that we do not know where the particle is. It is that the particle genuinely does not have a single definite position until the moment we look. This is called superposition, and it is one of the most fundamental principles of quantum mechanics. Think about this carefully, because it is crucial for understanding entanglement. In our everyday world, if you have a coin in a box, it is either heads or tails before you open the box. You just do not know which one. But in the quantum world, the coin is genuinely both heads and tails at the same time until you open the box. Both states exist simultaneously. They are both real. The coin is in a superposition of heads and tails. Only when you look, only when you make a measurement, does the coin snap into one definite state. This is not a metaphor. This is not a simplification for the sake of explanation. This is what the mathematics of quantum mechanics tells us, and every experiment we have ever performed confirms it. Particles genuinely exist in multiple states simultaneously until measurement forces them to choose. And here is the disturbing part. The choice is random. Completely, fundamentally, irreducibly random. When you measure a particle that is in a superposition of two states, which state it chooses is determined by nothing. No hidden mechanism, no secret variable, no cause. Pure, pristine randomness. This randomness is not like the randomness of a coin flip. When you flip a coin, the result is determined by physics. The force of your thumb, the air resistance, the height. In principle, if you knew everything about the initial conditions, you could predict the outcome. Quantum randomness is different. There is nothing to know. There are no initial conditions that determine the outcome. The universe itself does not know which result will occur until it happens. This distinction will become absolutely critical when we discuss why entanglement cannot send information. Now, quantum mechanics was not born overnight. It emerged in the early 20th century through the work of many brilliant physicists who were trying to understand phenomena that classical physics simply could not explain. Max Planck discovered that energy comes in discrete packets called quanta. Albert Einstein showed that light behaves as both a wave and a particle. Niels Bohr created a model of the atom with discrete energy levels. Werner Heisenberg developed matrix mechanics. Erwin Schrödinger created wave mechanics. Paul Dirac unified these approaches. Together, piece by piece, they built the most successful theory in the history of science. And I mean that literally. Quantum mechanics is not approximately correct. It is not mostly right with some errors around the edges. It is the most precisely tested theory ever created by human beings. Its predictions have been verified to 12 decimal places. That is like predicting the distance from Earth to the Moon and being accurate to within the width of a single atom. No other theory in any field of science comes close to this level of precision. Whatever quantum mechanics tells us about reality, it is telling us something profoundly correct. But here is the thing. Despite its incredible success, despite its perfect predictions, quantum mechanics disturbed many of the very people who created it. Einstein in particular was deeply uncomfortable with the idea that reality is fundamentally random, that particles do not have definite properties until measured, that the universe operates on probability rather than certainty. His famous quote, "God does not play dice with the universe," captures his resistance to this idea. Einstein believed that quantum mechanics must be incomplete, that there must be deeper variables, hidden from our view, that determine outcomes in advance. He believed that particles do have definite properties at all times, and that our inability to predict measurement outcomes simply reflects our ignorance of these hidden variables. This brings us to one of the greatest intellectual battles in the history of science. On one side stood Albert Einstein, arguing that reality must be definite, local, and deterministic. On the other side stood Niels Bohr, arguing that quantum mechanics is complete, that reality genuinely is probabilistic, and that particles truly do not have definite properties until measured. This debate would rage for decades. It would lead directly to the discovery of quantum entanglement. And it would ultimately be resolved by experiment, in a way that surprised everyone. The story really begins in 1935, when Einstein, along with his colleagues Boris Podolsky and Nathan Rosen, published one of the most important papers in the history of physics. Known as the EPRA paper, after the initials of its three authors, it presented what they believed was a devastating argument against the completeness of quantum mechanics. Their reasoning was elegant and appeared irrefutable. Here is what they argued. According to quantum mechanics, you can create two particles in a special state where their properties are perfectly correlated. For example, you can create two particles whose spins are guaranteed to be opposite. If one is spinning up, the other must be spinning down. But according to quantum mechanics, neither particle has a definite spin until measured. Both are in a superposition of up and down simultaneously. Now, said Einstein, suppose these two particles fly apart to opposite ends of the universe. You measure the spin of particle 1 and find it is up. Instantly, quantum mechanics tells us particle 2 becomes down. But how does particle 2 know that particle 1 was measured? How does it know to become down rather than up? Remember, they are separated by an enormous distance. No signal traveling at the speed of light or slower could have reached particle 2 in time. So either there is a faster-than-light signal connecting them, which would violate Einstein's own theory of relativity, or the particles had definite spins all along, and quantum mechanics is simply incomplete. It is missing the hidden variables that predetermine the outcomes. Einstein, Podolsky and Rosen concluded that quantum mechanics must be incomplete. The particles must carry hidden information that determines their measurement outcomes in advance. This hidden information travels with them from the moment of creation. When you measure one particle, you are not causing anything to happen to the other. You are simply revealing information that was determined from the start. Like reaching into a bag and pulling out a red ball, you know the remaining ball must be blue. No signal needed, no mystery, just pre-existing information being revealed. This seemed like an airtight argument. It was logical. It respected the speed of light limit. It preserved the common-sense notion that objects have definite properties whether we look at them or not. And for nearly 30 years, most physicists simply accepted it as a philosophical point and moved on. The debate between Einstein and Bohr seemed unresolvable by experiment. It appeared to be a matter of interpretation rather than physics. But they were wrong. In 1964, a physicist named John Stuart Bell proved that Einstein's position was not just a philosophical preference. It was a testable scientific claim, and Bell showed exactly how to test it. This is one of the most important moments in the history of physics, and it deserves our full attention. Bell's insight was profound in its simplicity. He realized that if hidden variables exist, if particles carry predetermined answers to all possible measurements, then there are mathematical limits on how strongly the measurements of two particles can be correlated. These limits are called Bell's inequalities. They are not complicated. They are basic probability theory. If two particles carry hidden instructions, then the statistical correlations between measurements in different directions cannot exceed certain values. But quantum mechanics predicts that these limits will be exceeded. Quantum mechanics predicts stronger correlations than any hidden variable theory can produce. This means the debate between Einstein and Bohr was not just philosophical. It was experimental. You could actually go into a laboratory, create entangled particles, measure them in various directions, calculate the correlations, and determine once and for all whether the results obey Bell's inequality or violate it. Let me explain this more concretely, because it is essential to understanding the whole picture. Imagine Alice and Bob each receive one particle from an entangled pair. They can each choose to measure their particle's spin in one of several directions. Let us say they can choose direction A, direction B, or direction C. Now, if hidden variables exist, then each particle carries a predetermined answer for every possible measurement direction. Before any measurement happens, particle 1 already knows it would be up if measured in direction A, down if measured in direction B, and up if measured in direction C. Similarly for particle 2. Bell showed that if this is true, if these predetermined answers exist, then the correlations between Alice's and Bob's results must satisfy certain mathematical constraints. The math is not difficult. It is essentially the same logic that tells you a person cannot be taller than 6 feet, shorter than 5 feet, and exactly 5'6" at the same time. There are logical constraints on what is possible. But quantum mechanics predicts correlations that violate these constraints. The quantum prediction says the correlations are stronger than any predetermined answers could produce. This means that if you run the experiment and find violations of Bell's inequality, you have proven that the particles did not have predetermined answers. They were genuinely undetermined until measurement. Einstein's hidden variables do not exist. And this is exactly what happened. In 1972, John Clauser and Stuart Friedman performed the first experimental test of Bell's inequality. Their results violated Bell's inequality, matching the predictions of quantum mechanics. In 1982, Alain Aspect performed a much more rigorous test with better controls. Again, Bell's inequality was violated. Again, quantum mechanics was correct. The experiments were repeated with increasing precision throughout the 1980s, 1990s, and 2000s. Every single time, the same result. Bell's inequality violated. Hidden variables ruled out. Einstein was wrong. But scientists are careful people. They worried about loopholes. Maybe the experiments had subtle flaws that could explain the results without abandoning hidden variables. There were 3 main loopholes that concerned physicists. The detection loophole asked whether the particles that were successfully detected were somehow a biased sample. The locality loophole asked whether the measurement choices could have been influenced by signals traveling between the detectors. And the freedom of choice loophole asked whether the experimenter's choices of measurement directions were truly free and random. One by one, these loopholes were closed. In 2015, a team at the Delft University of Technology performed the first experiment that simultaneously closed all major loopholes. Their result was unambiguous. Bell's inequality was violated. No hidden variables can explain the quantum correlations. The particles genuinely do not carry predetermined answers. Einstein's local realism is experimentally falsified. In 2022, the Nobel Prize in Physics was awarded to Alain Aspect, John Clauser, and Anton Zeilinger for their experimental work establishing the violation of Bell's inequalities and pioneering the field of quantum information science. This was not a controversial award. The physics community had long accepted that Bell's theorem and its experimental verification represent one of the most profound discoveries about the nature of reality. So where does this leave us? Let me make sure the picture is clear. We have proven, experimentally, that entangled particles do not carry hidden instructions. They do not have predetermined measurement outcomes. When 2 particles are entangled, they exist in a shared quantum state where neither particle individually has a definite value until measured. The correlation between them is not because they agreed on their answers in advance. The correlation is something deeper, something that has no analogy in everyday experience, something genuinely new that quantum mechanics has revealed about reality. And yet, despite this deep, mysterious, experimentally verified connection between entangled particles, you cannot use it to send information. This is the puzzle we need to solve. We now have all the background we need to understand why. But first, let me address a very common and very wrong explanation that people often give for entanglement. You will hear people say something like this: entanglement is simple. It is like putting one red sock and one blue sock into two different boxes. You send one box to New York and one to Tokyo. When you open the box in New York and see a red sock, you instantly know Tokyo has the blue sock. No mystery. No faster than light anything. Just pre-existing information. This analogy is wrong. Dead wrong. And Bell's theorem is precisely what proved it wrong. The sock analogy is the hidden variable theory. It is Einstein's position. And it has been experimentally falsified. If entanglement were just like socks in boxes, Bell's inequality would not be violated. But it is violated. The correlations in quantum entanglement are stronger than anything the sock analogy can produce. The sock analogy assumes the colors were determined when the socks went into the boxes. Quantum mechanics says the particles did not have determined values when they separated. The correlation is not because they agreed in advance. It is something else entirely. Something that only becomes apparent when you compare measurements in different directions, at different angles. In those cases, the quantum correlations exceed what any pre-agreement could produce. So entanglement is genuinely mysterious. The connection is real and goes beyond any classical explanation. The particles truly are connected in a way that has no classical analog. And yet, maddeningly, beautifully, profoundly, this connection cannot be used to send a message. Now let us understand why. Let us finally tackle the central question of this entire exploration. Why does quantum entanglement refuse to send information? The answer has several layers, and each layer adds depth to our understanding. Let me start with the most direct and intuitive layer, and then we will go deeper. The most immediate reason is randomness. Remember what we discussed about quantum measurements being fundamentally random? This is the key. When Alice measures her entangled particle, she gets a random result. Completely, unpredictably, fundamentally random. She might get up. She might get down. The probability is exactly 50-50, and nothing in the universe, not even the laws of physics themselves, can tell you in advance which one she will get. Now, when Bob measures his entangled particle, he also gets a random result, also 50-50, also completely unpredictable. If they are measuring in the same direction, their results will be perfectly anti-correlated. When Alice gets up, Bob gets down. When Alice gets down, Bob gets up. Every single time. But here is the crucial point. Bob has no way of knowing, from his measurement alone, what Alice did. All he sees is a random sequence of ups and downs. Half the time up, half the time down, in no discernible pattern. Think about what this means for communication. For Alice to send a message to Bob using entanglement, she would need to be able to control what Bob sees. She would need to make some choice on her end that changes what Bob observes on his end. But she cannot do this. Because no matter what Alice does, no matter how she measures her particle, no matter what direction she chooses, no matter whether she measures at all or not, Bob's results remain the same. Random, 50-50. Up and down with equal probability in any direction he chooses to measure. This deserves emphasis because it is the heart of the answer. Bob cannot tell, from his measurements alone, whether Alice has measured her particle or not. He cannot tell what direction she measured in. He cannot tell anything about what Alice did. His local measurement statistics are completely independent of Alice's actions. No matter what experiment Bob performs on his particle alone, the results are random and independent of anything Alice does or does not do. To actually see the entanglement, to actually observe the correlations, Alice and Bob must compare their results. They must communicate. They must send their measurement records to each other using ordinary classical communication, traveling at or below the speed of light. Only then, when they put their data side by side, do the correlations become visible. Only then can they see that every time Alice got up, Bob got down, and vice versa. This is the profound irony. The entanglement correlations are real. They are instant. They transcend distance. But they are invisible to either party alone. They exist only in the comparison. And the comparison requires classical communication. Ordinary communication that obeys the speed of light. Let me make this even more concrete with an example. Suppose Alice wants to send the message hello to Bob using entanglement. What would she need to do? She would need to somehow encode that message into something that affects what Bob sees when he measures his particle. But her measurement outcomes are random. She gets up or down with equal probability. She cannot choose to get up when she wants to send a 1 and down when she wants to send a 0. The outcomes are not up to her. The universe decides, randomly, what she gets. You might think, well, what if she chooses to measure or not measure? If she measures, Bob's particle becomes definite. If she does not measure, it stays in superposition. Cannot Bob detect the difference? The answer is no. Bob cannot tell whether his particle is in a definite state or in superposition. Those two situations are experimentally indistinguishable from a single measurement. The probabilities are the same either way. Whether Alice measured or not, Bob gets up 50% of the time and down 50% of the time. No difference whatsoever. What if Alice measures in a different direction? What if she measures up-down versus left-right? Surely this changes something about Bob's particle. And indeed it does, in a certain mathematical sense. If Alice measures in the up-down direction and gets up, Bob's particle becomes down in the up-down direction. If Alice measures in the left-right direction and gets left, Bob's particle becomes right in the left-right direction. But here is the thing. If Bob measures in the up-down direction regardless of what Alice did, he gets up 50% of the time and down 50% of the time. Always, no matter what Alice did. Her choice of measurement direction does not affect his probability distribution. This is not obvious. This is not intuitive. But it is mathematically provable, and it is experimentally verified. The formal statement is called the no communication theorem, sometimes also called the no signaling theorem. It states that the local measurement statistics on one half of an entangled pair are completely independent of any operation performed on the other half. This is a rigorous mathematical theorem derivable directly from the axioms of quantum mechanics. Let me explain the mathematics in an accessible way. In quantum mechanics, the state of a system is described by what is called a density matrix. For a two-particle entangled system, there is a joint density matrix that describes both particles together. Now, if you want to know the statistics of measurements on Bob's particle alone, you perform what is called a partial trace. You trace out Alice's part of the system. What remains is called the reduced density matrix for Bob's particle. The no communication theorem proves that Bob's reduced density matrix is unchanged by anything Alice does to her particle. Whether she measures it, does not measure it, measures it in any direction, performs any quantum operation on it, or throws it into a black hole. Nothing she does changes Bob's reduced density matrix. And since Bob's reduced density matrix determines all possible measurement statistics on his particle, nothing Alice does can change any outcome that Bob could observe. This is not a matter of our current technology being insufficient. This is not a challenge that future engineers might overcome. This is a mathematical consequence of the fundamental structure of quantum mechanics. As long as quantum mechanics is correct, and remember it is the most precisely verified theory in all of science, information cannot travel through entanglement. The theorem is as solid as the theory itself. Now you might ask, what if we find some way around this? What if there is some operation Alice can perform that the no communication theorem does not cover? The answer is that the theorem covers everything. Every possible physical operation that quantum mechanics allows. Every unitary transformation, every measurement in any basis, every quantum channel, they are all covered. There is no loophole. There is no back door. The proof is complete and exhaustive. Let me approach this from yet another angle to drive the point home. Think about what would happen if entanglement could send information. If Alice could somehow influence Bob's measurement results, then she could send a message faster than light. But Einstein's special relativity tells us that faster-than-light communication leads to logical paradoxes. Specifically, it leads to situations where effects can precede their causes, where Bob receives a message before Alice sends it, where you could send information to your own past. This is not merely strange or counterintuitive. This is logically contradictory. It leads to genuine paradoxes, not just weird scenarios. If you can send information to the past, you can create situations that are self-contradictory. You can send a message saying, "Do not send this message," which means the message was never sent, which means you never received it, which means you did send it, and so on forever. No consistent physical theory can allow this. So the no communication theorem is not just a quirk of quantum mechanics. It is a deep consistency requirement. If entanglement could send information, either quantum mechanics or special relativity would have to be wrong. And both are verified to extraordinary precision. They are compatible precisely because entanglement does not transmit information. This is not a coincidence, it reflects a deep harmony in the laws of physics. Let me pause here and make sure we have the full picture of what we have established so far. We know that entangled particles exhibit correlations that are instantaneous across any distance. We know these correlations are not due to hidden variables or pre-existing information. We know the correlations are genuinely quantum mechanical, exceeding anything classical physics can produce. But we also know that these correlations cannot be used to communicate because they are hidden behind a veil of randomness that neither party can pierce alone. The correlations are real, but invisible to either observer individually. They exist only in the joint statistics, only in the comparison. And that comparison requires ordinary, speed-of-light limited communication. This is the resolution. This is why the universe can have instant non-local correlations without allowing faster-than-light communication. The correlations are symmetric, random, and only visible in retrospect. Now I want to go even deeper. I want to address some of the more subtle objections that clever people raise when they first encounter this result. Because the obvious follow-up question is, why can't Alice control her measurement outcome? Why is quantum randomness truly uncontrollable? Is this really fundamental, or might there be some way, even in principle, to beat the randomness? This question takes us to the very heart of quantum mechanics. The randomness in quantum measurement is not like any other randomness we encounter. It is not randomness from ignorance, where if we knew more we could predict the outcome. It is not randomness from complexity, where the system is too complicated to calculate, but in principle deterministic. It is what physicists call intrinsic randomness. Randomness that exists at the most fundamental level of reality. Randomness that is not caused by anything. Randomness that has no explanation, no hidden mechanism, no deeper layer. How do we know this? We know because of Bell's theorem. If the randomness were due to our ignorance of some hidden variable, then those hidden variables would produce measurement correlations that obey Bell's inequality. But Bell's inequality is violated. Therefore, the randomness is not due to hidden variables. It is fundamental. There is nothing beneath it, nothing causing it, no pattern to discover, no code to crack. This means that even in principle, with technology far beyond anything we can imagine, you cannot control quantum measurement outcomes. You cannot force a particle to be spin up rather than spin down. You cannot choose what you get. The universe does not allow it. This is not because of some barrier we have not yet overcome. It is because there is genuinely no mechanism that produces the outcome. The outcome simply happens, randomly, at the moment of measurement, controlled by nothing. And this fundamental uncontrollability is exactly what prevents communication through entanglement. Since Alice cannot choose her outcomes, she cannot encode any information into them. She is at the mercy of quantum randomness, just like Bob. Both of them see random sequences of results. Neither can influence what they see or what the other person sees. The entanglement creates a correlation between their random sequences, but neither person can control or even detect that correlation without communicating classically. There is another subtle but important point here. You might wonder, what if Alice does not try to control her specific outcomes, but instead tries to influence the statistical pattern of Bob's results? For example, what if measuring in one direction causes Bob's results to have a slightly different pattern than measuring in another direction? The no communication theorem rules this out completely. Not just the individual outcomes, but the entire probability distribution of Bob's results is independent of Alice's actions. Every statistical property, every moment, every pattern, every conceivable signal, all of it is unchanged by anything Alice does. This completeness of the no communication theorem is remarkable. It does not just say you cannot send specific messages, it says you cannot send any information whatsoever. Not a single bit. Not even a statistical whisper. Bob's world is utterly unaffected by Alice's choices from his local perspective. The only thing that connects them is the correlation, and the correlation is invisible locally. Now let me address another common question that arises at this point. People often ask, what about quantum teleportation? They have heard that scientists can teleport quantum states from one place to another using entanglement. Does this not mean entanglement can send information? The answer is no, and understanding why reveals something beautiful about the structure of physics. Quantum teleportation is a real protocol. It works. It has been demonstrated experimentally many times. It allows Alice to transfer an unknown quantum state from her location to Bob's location. But here is the key. It requires classical communication as part of the protocol. Without that classical communication channel, the teleportation does not work. Here is how it works in simplified form. Alice has an unknown quantum state she wants to send to Bob. She also shares an entangled pair with Bob. She performs a special joint measurement on her unknown state and her half of the entangled pair. This measurement gives her one of 4 random results. She then sends Bob a classical message using regular communication, telling him which of the 4 results she got. This message is just 2 bits of information, 00, 01, 10, or 11. Based on this message, Bob performs one of 4 operations on his half of the entangled pair. And then his particle becomes identical to Alice's original unknown state. Notice what happened. The entanglement was essential to the protocol. Without it, teleportation would be impossible. But the classical communication was also essential. Without it, Bob does not know which operation to perform, and his particle remains in a random state. The information about the quantum state was transmitted partly through the entanglement and partly through the classical channel. Neither alone is sufficient, and the classical communication travels at most at the speed of light. so the overall teleportation cannot be faster than light. This is a perfect illustration of the general principle. Entanglement is an incredibly useful resource. It enables things that are otherwise impossible. But it cannot replace classical communication. It can only supplement it. The no-communication theorem remains inviolate. Let me now take you into an even deeper layer of understanding. We have established that entanglement cannot send information, and we have seen the mechanism through which this works, namely the uncontrollable randomness of quantum measurement. But can we understand more deeply why the universe is built this way? Is there a deeper principle at work? One way to think about this is through the lens of causality. The principle of causality says that causes precede their effects. If information could travel faster than light, this principle would be violated because, according to special relativity, what counts as before and after depends on your frame of reference. Two events that are simultaneous in one reference frame occur in different orders in other reference frames. If one of those events could cause the other, you would have situations where the effect comes before the cause in some reference frames. This is unacceptable in any consistent physical theory. So the no-communication theorem is, in a sense, the universe protecting causality. Quantum mechanics allows non-local correlations, but it wraps them in just enough randomness to prevent any causal influence from traveling faster than light. The randomness is not an accident. It is not a defect. It is precisely calibrated to prevent faster-than-light signaling, while still allowing the strange, beautiful, experimentally verified correlations of entanglement. This perspective reveals something profound. The randomness of quantum mechanics and the impossibility of faster-than-light communication are not separate features. They are the same feature viewed from different angles. The randomness ensures the no signaling, and the no signaling requires the randomness. They are two sides of one coin. Remove the randomness, and you get faster than light communication. Remove the no signaling constraint, and you lose the randomness. The universe maintains both simultaneously, in perfect balance. Some physicists have taken this even further and suggested that the no signaling principle might be more fundamental than quantum mechanics itself. In other words, maybe we should not ask why quantum mechanics prevents faster than light signaling. Maybe we should ask what theories are consistent with no faster than light signaling, and find that quantum mechanics is one of them. From this perspective, the laws of quantum mechanics are partially determined by the requirement that communication not exceed the speed of light. This is an active area of research in quantum foundations, and it connects to deep questions about why the laws of physics have the form they do. But the key takeaway for our purposes is that the no-communication theorem is not some arbitrary rule tacked on to quantum mechanics. It emerges naturally and inevitably from the mathematical structure of the theory, and it is deeply connected to the consistency of spacetime and causality. Now, let me take you on a slightly different journey. Let us explore what the different interpretations of quantum mechanics say about entanglement and why communication through it is impossible. Because it turns out that every major interpretation of quantum mechanics agrees on this point, even though they disagree about almost everything else. This unanimity is telling. The Copenhagen interpretation, which was championed by Niels Bohr and remains the most widely taught version of quantum mechanics, says that the wave function of a quantum system represents our knowledge of that system rather than an objective reality. When we measure a particle, the wave function collapses, reflecting our updated knowledge. In this interpretation, asking what happens to Bob's particle when Alice measures hers is somewhat meaningless. The wave function is not a physical thing that changes. It is a mathematical tool for calculating probabilities. Bob's probabilities are unaffected by Alice's measurement because there is nothing physical traveling between them. The correlations emerge only when results are compared, as a statistical property of the shared quantum state. The many-worlds interpretation, developed by Hugh Everett in 1957, takes a radically different view. It says the wave function never collapses. Instead, when a measurement occurs, the universe splits into multiple branches, one for each possible outcome. In one branch, Alice gets up. In another branch, Alice gets down. Both branches are equally real. Both continue to exist. When Alice measures her particle, her universe splits. But Bob's universe has not yet split in a corresponding way until he makes his own measurement. And when he does, his universe also splits. The correlations between Alice and Bob only manifest when they meet and compare results, which happens in specific branches. In this interpretation, there is no faster-than-light influence, because nothing actually happens to Bob's particle when Alice measures. The universe simply branches, and the branches sort themselves out later when information travels at light speed or slower. The pilot wave interpretation, also known as Bohmian mechanics, takes yet another approach. In this interpretation, particles always have definite positions, guided by a real physical wave called the pilot wave. The pilot wave is non-local, meaning it connects distant particles. When Alice measures her particle, the pilot wave changes, instantly affecting Bob's particle. There is a non-local influence in this interpretation. But even in Bohmian mechanics, this non-local influence cannot be used to send signals. The pilot wave changes in a way that preserves the statistical randomness of Bob's outcomes. The non-locality is real, but hidden. It influences the outcomes, but does not allow control or communication. This is built into the mathematical structure of the pilot wave. The relational interpretation, proposed by Carlo Rovelli, suggests that quantum states are not absolute, but relational. A particle does not have properties in an absolute sense. It has properties relative to a specific observer. From this perspective, entanglement is a correlation between how one particle appears to one observer and how the other particle appears to another observer. Communication is impossible because these relational properties only become correlated when the observers interact, which requires classical communication. What is remarkable is that despite their radically different metaphysical commitments, all these interpretations agree on the observable facts. They all agree that entanglement cannot send information. They all agree on the predictions of quantum mechanics. They differ only in their stories about what is really happening behind the scenes. But the no communication theorem holds in every single one of them. This suggests that the impossibility of communicating through entanglement is not interpretation dependent. It is a robust feature of quantum reality itself, independent of how we choose to interpret that reality. Let us now turn our attention to some of the most common misconceptions about quantum entanglement and communication, because I think it is important to clear these up explicitly. The first and most prevalent misconception is that entanglement means the particles are communicating with each other. This is how it is often portrayed in popular science, and especially in science fiction. Two entangled particles are described as having some kind of invisible thread or channel between them through which information flows. This is simply not what the physics says. There is no signal, no channel, no thread. The correlations emerge from the shared quantum state the particles were born in, not from any ongoing communication between them. The second misconception is that our current technology is simply not advanced enough to use entanglement for communication, and that future technology might crack the code. This fundamentally misunderstands the nature of the limitation. The no communication theorem is not a technological barrier. It is a mathematical theorem. It follows directly from the axioms of quantum mechanics. To violate it, you would need quantum mechanics itself to be wrong. And quantum mechanics is the most tested theory in physics. The limitation is not about engineering. It is about the fundamental structure of reality. The third misconception is that advanced alien civilizations might have figured out how to use entanglement for instant communication across the galaxy. This is a popular science fiction idea appearing in novels and films. But physics does not have different rules for different civilizations. The no communication theorem applies universally. It does not matter how intelligent or technologically advanced a civilization is. The mathematics is clear. If quantum mechanics is correct, entanglement cannot send information. Period. An alien civilization can no more use entanglement for communication than they can make 2 + 2 = 5. The fourth misconception is that quantum mechanics proves consciousness affects physical reality, and that perhaps consciousness could be used to push information through entanglement. This comes from a misunderstanding of the measurement problem. When physicists say that observation collapses the wave function, they do not mean that human consciousness is required. Any sufficiently complex interaction with the environment causes decoherence, which produces the same effect as measurement. A detector, a photon, a stray air molecule, all of these can measure a quantum system. Consciousness has nothing to do with it, and even if it did, the no communication theorem would still hold, because it makes no assumptions about what causes measurement. It applies regardless. The fifth misconception is more subtle. Some people suggest that if you could clone a quantum state, you could use entanglement to communicate. The idea is that Bob receives many copies of his particle, measures each one, and from the statistics determines what Alice did. But quantum mechanics also forbids cloning. The no cloning theorem, proven in 1982, states that it is impossible to create an identical copy of an arbitrary unknown quantum state. This is not a coincidence. The no cloning theorem and the no communication theorem are deeply related. If cloning were possible, communication through entanglement would become possible. So the universe closes both doors simultaneously. Now I want to explore something fascinating that sits at the frontier of our current understanding. What does entanglement tell us about the nature of space itself? This is where physics gets truly mind-bending, and it connects to some of the deepest questions about the universe. In 2013, physicists Juan Maldacena and Leonard Susskind proposed a remarkable conjecture known as ER equals EPR. The ER refers to Einstein-Rosen bridges, which are what physicists call wormholes, theoretical tunnels through spacetime connecting distant regions. The EPR refers to the Einstein-Podolsky-Rosen paper we discussed earlier, which first described quantum entanglement. Maldacena and Susskind propose that every pair of entangled particles is connected by a tiny wormhole, that entanglement and wormholes are the same phenomenon viewed from different perspectives. This is a conjecture, not a proven theorem, but it has generated enormous excitement in the theoretical physics community because it suggests a deep connection between quantum mechanics and the geometry of spacetime. If ER equals EPR is correct, then entanglement is not just a quantum phenomenon. It is related to the very fabric of space and time. Even more remarkably, some physicists have proposed that spacetime itself might emerge from entanglement, that the smooth, continuous space we experience is actually built from a vast network of quantum entanglement between microscopic degrees of freedom. In this picture, space is not fundamental. Entanglement is fundamental. Space is a consequence. This is speculative, cutting-edge theoretical physics. It is not yet established, but it gives you a sense of how profound entanglement is. It may not be able to send information, but it might be the very thread from which the fabric of reality is woven. The inability to communicate through entanglement takes on a different character in this context. It is not a limitation of entanglement. It is a feature of how entanglement builds space. The very notion of distance, of here and there, of needing to send information from one place to another might itself emerge from the entanglement structure. You cannot use entanglement to send information across space because entanglement is what creates space in the first place. This is deep, speculative territory, and I want to be clear that it is not yet established science. But it represents one of the most exciting directions in theoretical physics today, and it gives us a glimpse of how the no-communication theorem might fit into an even larger picture. Let me now turn to what entanglement can do, because it is important to appreciate that even without the ability to send information faster than light, entanglement is an extraordinarily useful resource. It enables technologies that are impossible without it, and these technologies are not science fiction. They exist today in real laboratories, and some are already being deployed commercially. The most mature application of entanglement is quantum key distribution. This is a method for generating unbreakable encryption keys between two parties. Here is how it works. Alice and Bob share many pairs of entangled particles. They each measure their particles in randomly chosen directions. Then they use a classical channel to compare which directions they chose, without revealing their results. For the cases where they happen to choose the same direction, their results are perfectly correlated. These correlated results become their shared secret key. The beauty of this system is that any eavesdropper who tries to intercept the entangled particles necessarily disturbs them. Entanglement is extraordinarily fragile. Any interaction with a third party destroys the entanglement, which changes the correlations. Alice and Bob can detect this disturbance by checking a sample of their results. If the correlations are preserved, they know no one intercepted their particles, and their key is secure. If the correlations are disturbed, they know an eavesdropper was present, and they discard that key. This is not theoretical. China launched the Messier satellite in 2016 and used it to demonstrate quantum key distribution over distances of more than 12,100 kilometers. In 2017, they established a quantum-secured video link between Beijing and Vienna using this technology. Multiple countries are now investing billions of dollars in quantum communication networks. The technology works precisely because entanglement cannot send information. The entangled particles cannot be intercepted without detection, because the no-cloning theorem prevents perfect copying, and any measurement disturbs the state. Another major application is quantum computing. Entanglement is one of the key resources that gives quantum computers their power. A quantum computer with n entangled quantum bits can explore 2 to the power n possibilities simultaneously, compared to a classical computer which can only explore them one at a time. For certain problems, this exponential advantage allows quantum computers to solve in minutes what would take classical computers billions of years. The problems quantum computers are expected to excel at include simulating molecular and chemical systems for drug discovery, optimizing complex logistics and scheduling problems, breaking certain types of encryption, training machine learning models, and modeling financial markets. All of these applications rely on entanglement between the quantum bits inside the computer. Without entanglement, a quantum computer offers no advantage over a classical one. Quantum teleportation, which we discussed earlier, is the foundation of future quantum networks. By teleporting quantum states from one node to another, physicists envision building a quantum internet that enables distributed quantum computing, blind quantum computing, where a client can use a server's quantum computer without revealing their data, and perfectly secure communication networks. Quantum sensing is another rapidly developing field. Entangled particles can be used to make measurements with precision beyond what is possible with unentangled particles. This has applications in medical imaging, where entangled photons can create sharper images with lower radiation doses. It has applications in gravitational wave detection, where entangled light improves the sensitivity of interferometers. And it has applications in navigation, where quantum sensors can detect rotation and acceleration with extraordinary precision. All of these applications use entanglement as a resource. They exploit its strange properties in clever ways that do not require or attempt to send information through it. They work with the no communication theorem rather than against it. And they represent some of the most exciting technological developments of our time. Now, let me take us to an even more philosophical level. I want to explore what the no communication theorem tells us about the nature of information itself. Because the concept of information is central to this entire discussion, and understanding it precisely reveals something deep about reality. In physics, information is not just data or facts, it is something more fundamental. Information is the ability to distinguish between different possibilities. When Alice sends a message to Bob, she is reducing Bob's uncertainty about something. She is eliminating possibilities from his perspective. Before the message, Bob did not know something. After the message, he does. Information has traveled from Alice to Bob because his state of knowledge has changed in a way that correlates with Alice's actions. With entanglement, this transfer of knowledge does not happen. Bob's local state of knowledge is unchanged by anything Alice does. He sees random outcomes regardless. His uncertainty remains the same. No possibilities are eliminated from his perspective by Alice's actions. Therefore, no information has traveled. This is a precise, operational definition of information that makes the no communication theorem not just mathematically clear, but conceptually transparent. Information, in the physics sense, requires the ability to distinguish between different possible messages. If Alice wants to send a 1 or a 0, Bob must be able to tell which one she sent by performing some measurement on his end. But with entanglement, Bob's measurement statistics are identical whether Alice sent a 1 or a 0. He literally cannot tell the difference. The two situations are physically, mathematically, experimentally indistinguishable from Bob's perspective. Therefore, no information has been transmitted. This connects to a deeper principle in physics called the Holevo bound, which sets fundamental limits on how much classical information can be extracted from quantum systems. The Holevo bound tells us that even with the most clever possible measurement strategy, you cannot extract more than n classical bits of information from n quantum bits. Entanglement does not increase this limit. It does not give you extra bandwidth for classical information. It is a different kind of resource entirely, useful for computation and security, but not for communication. There is something almost poetic about this. The universe creates these extraordinary connections between distant particles. Connections that transcend space. Connections that are instantaneous. But the connections carry no news. They transmit no updates. They send no messages. They are correlations without communication. Connections without content. Links without language. And yet they are real. Deeply, fundamentally real. More real than any classical correlation. Stronger than any prearranged agreement. Verified to extraordinary precision. The universe is showing us something. It is showing us that reality is more interconnected than we imagined, but also more subtle. The connections exist, but they are not the kind of connections our everyday intuitions prepare us for. They do not send signals, they do not carry information. They exist in a realm beyond communication, in the pure mathematical structure of quantum states. Let me now discuss some of the more recent experiments that have pushed our understanding of entanglement to new limits. These experiments help solidify everything we have discussed and show that the physics community continues to probe and test these ideas with ever-increasing precision. In 2017, the Chinese team behind the Messier satellite demonstrated entanglement distribution over 203 kilometers. They created entangled photon pairs on the satellite and sent one photon to a ground station in Delinga and the other to a ground station in Lijiang. The photons maintained their entanglement despite traveling through space and the atmosphere. Bell's inequality was violated at a significance level that ruled out local hidden variables beyond any reasonable doubt. This experiment confirmed that entanglement works over enormous distances and that the no-communication theorem applies regardless of how far apart the particles are. In 2018, researchers at the University of Glasgow captured the first photograph of quantum entanglement. Using a special camera that could detect individual photons and record their correlations in real time. They created an image showing entangled photons violating Bell's inequality. The image showed a pattern that could only be explained by entanglement, not by any classical correlation. It was a striking visual confirmation of a phenomenon that had previously been accessible only through statistical measurements. In 2019, a team at the University of Science and Technology of China demonstrated quantum teleportation over a fiber optic distance of 44 kilometers. This was an important step toward building practical quantum communication networks. The teleportation required both entanglement and classical communication, perfectly illustrating the principle we have discussed. The entanglement alone could not do the job. Classical communication was essential. In 2020, researchers created entanglement between particles separated by 50 kilometers of optical fiber with extremely low error rates. This demonstrated that entanglement-based quantum networks are technically feasible at metropolitan scales. The technology is ready. The question is now about engineering and deployment, not about fundamental physics. In 2022, as mentioned earlier, the Nobel Prize was awarded for the experimental foundations of quantum information science. The committee specifically cited the verification of Bell inequality violations and the development of quantum information tools based on entanglement. This was the scientific establishment's definitive acknowledgement that quantum entanglement is real, is useful, and is understood well enough to form the basis of new technologies. All of these experiments confirm the picture we have built throughout this exploration. Entanglement is real, it works over any distance, it is stronger than any classical correlation, but it cannot send information. The no-communication theorem holds with exquisite precision in every experiment ever performed. To address one more fascinating aspect of this topic, the question of whether the no-communication theorem could ever be wrong. Could some future discovery overthrow it? Could we find a loophole? This is a question worth taking seriously, because science is always provisional. No theory is beyond challenge. But there are strong reasons to believe the no-communication theorem is on very solid ground. First, it is a mathematical theorem, not an empirical observation. It follows logically from the axioms of quantum mechanics. To violate it, you would need to change the axioms themselves. This is not impossible in principle, but it would require a complete revolution in physics, not a minor adjustment. Second, the theorem is connected to other fundamental principles, including special relativity and causality. Violating the no-communication theorem would require violations of relativity, which would create paradoxes and contradictions throughout physics. It would unravel the fabric of our understanding. Third, every experiment ever performed is consistent with the theorem. There is no unexplained data, no anomalous result, no hint of information traveling through entanglement. The experimental evidence is entirely consistent with the theory. Fourth, even speculative theories of quantum gravity, such as string theory and loop quantum gravity, maintain the no-communication theorem. These are theories that go beyond standard quantum mechanics, that attempt to unify quantum mechanics with general relativity. Yet even in these more fundamental theories, the principle that entanglement cannot send information is preserved. This suggests it is a very deep and robust feature of reality. That said, science must remain open to surprises. If someone performed an experiment that convincingly demonstrated information traveling through entanglement, that would be one of the most momentous discoveries in the history of science. It would overthrow not just quantum mechanics, but special relativity as well. It would require us to completely rebuild our understanding of space, time, and causality. The chances of this are extraordinarily small, but we should never say never in science. What is more likely is that our understanding will deepen. We may discover deeper reasons why the no communication theorem holds. We may discover its connection to quantum gravity and the emergence of spacetime. We may find that it is a consequence of an even more fundamental principle that we have not yet identified. This is the direction current research is heading, and it promises profound insights, even if the theorem itself remains unshaken. Let me now bring some of these threads together and talk about what all of this means for our understanding of reality. Quantum entanglement has revealed something extraordinary about the universe. It has shown us that reality is non-local, that distant parts of the universe can be connected in ways that transcend space, that the correlations between separated systems can exceed anything that local, realistic physics can produce. This is a genuine discovery about the nature of reality, verified beyond reasonable doubt. But the universe has also shown us that this non-locality has a very specific character. It is what physicists call peaceful non-locality. It exists, but it does not disturb the causal structure of spacetime. It does not allow faster than light signals. It does not enable communication across distances without light speed delay. It is non-locality without signaling. Correlation without communication. Connection without causation. This tells us something profound about the architecture of reality. The universe is built with layers of structure that fit together in precisely calibrated ways. Quantum mechanics allows non-local correlations. Special relativity forbids faster than light signals. These two requirements are compatible, but only barely. Only if the non-local correlations are wrapped in exactly the right kind of randomness. Nature threads the needle perfectly. It gives us entanglement that is real and powerful and strange, but packages it so that causality is preserved. Is this a coincidence? Is it just an accident that quantum mechanics happens to preserve relativistic causality? Most physicists believe it is not. They believe there is a deeper principle at work. Something that explains why the laws of physics take this particular form. Some believe it is a principle about information itself. Some believe it is related to the consistency of space-time geometry. Some believe it emerges from even more fundamental structures that we have not yet discovered. This is one of the great open questions in physics. And entanglement is at the center of it. The fact that entanglement refuses to send information is not just a technical curiosity. It is a clue. A clue about the deepest structure of reality. About why the universe is the way it is, rather than some other way. About how quantum mechanics and gravity fit together. About the nature of space and time themselves. Let me also discuss how this relates to the concept of free will and determinism. Because this is another area where people often get confused about what quantum entanglement implies. Some people argue that if entangled particles are correlated instantly, this means the future is predetermined. If measuring one particle instantly determines the other, does this not imply everything is already decided? The answer is no. The correlations are established at the moment of measurement, not before. Before measurement, neither particle has a definite state. The future is genuinely open, genuinely undetermined, until the moment of measurement. and the measurement outcome is genuinely random, not predetermined by any hidden variable. Others argue the opposite, that quantum randomness proves free will. If outcomes are not predetermined, then we are free to choose. But this is also too simple. Randomness is not the same as freedom. A random coin flip is not making a free choice. The relationship between quantum mechanics and free will remains deeply contested, and entanglement does not resolve it in either direction. What entanglement does show us is that the simple picture of reality, where things have definite properties and causes precede effects in a straightforward chain, is wrong. Reality is more subtle, more interconnected, and more strange than this simple picture allows. But it is not chaos either. It has precise mathematical structure. It obeys exact laws. It is predictable in its statistics, even when individual events are random. It is a reality that requires us to expand our concepts, not abandon rational inquiry. Now let me address one more topic that I think is important for completing our picture. The relationship between entanglement, decoherence, and the classical world we experience. If quantum mechanics is the fundamental theory of reality, and entanglement is one of its key features, why do we not experience entanglement in our everyday lives? Why does the world around us seem classical, deterministic, and local? The answer is decoherence. Decoherence is the process by which quantum systems become entangled with their environment, losing their quantum properties from the perspective of any single observer. When a quantum particle interacts with air molecules, photons, dust particles, and all the other components of a macroscopic environment, it becomes entangled with them. Its quantum state spreads out into the environment, becoming impossibly diluted. The delicate quantum correlations become distributed among trillions of environmental degrees of freedom, making them completely undetectable in practice. This is why we do not experience quantum weirdness in everyday life. Not because quantum mechanics stops working at large scales, but because decoherence hides quantum effects from us. The quantum mechanics is still there, still operating, but its effects are distributed across so many particles that they become invisible to any practical measurement. Decoherence also explains why entanglement is so fragile in experiments. Any interaction between an entangled particle and its environment destroys the entanglement by spreading it into the environment. This is why quantum experiments must be performed in extreme isolation, with particles shielded from all environmental interactions. It is why quantum computers must operate at temperatures near absolute zero, where thermal fluctuations are minimized. It is why maintaining entanglement over long distances is an enormous technical challenge. But it also provides another perspective on why entanglement cannot send information in practice. Even in situations where the no-communication theorem might seem theoretically challengeable, decoherence steps in as an additional barrier. Any real-world implementation of entanglement involves some decoherence, which further degrades the correlations and makes communication even more impossible. Nature has multiple redundant safeguards against faster-than-light signaling. Let me now bring up something truly fascinating about the relationship between entanglement and quantum computing, because this further illustrates what entanglement can and cannot do. In a quantum computer, entanglement between quantum bits is one of the key resources that enables exponential speedup over classical computers. But it is important to understand exactly what role entanglement plays and what it does not do. A quantum computer does not work by sending information faster than light between its quantum bits. It works by creating superpositions and entanglement that allow it to explore many computational paths simultaneously. The entanglement creates correlations between different parts of the computation that allow interference, where wrong answers cancel out and correct answers reinforce each other. At the end of the computation, When you measure the output, you get a random result from the superposition. But the interference has been carefully arranged so that the random result is, with high probability, the correct answer to the computational problem. The randomness is still there. You cannot control which specific result you get, but the probability has been concentrated on the correct answer. This is a brilliant use of quantum mechanics that respects all its rules. It does not try to fight the randomness. It works with it. It shapes the probability distribution through interference and entanglement so that the randomness naturally produces useful answers. This is the paradigm of quantum computing, not overcoming quantum limitations, but exploiting quantum features within those limitations. And notice that nothing about quantum computing violates the no communication theorem. All the quantum bits are in the same computer at the same location. No information is being sent faster than light. The entanglement is a resource for computation, not for communication. The distinction is clear and important. Let me take another angle on our central question. I want to explore what happens if we consider the entangled system from the perspective of quantum field theory, which is the more fundamental framework within which quantum mechanics operates. Quantum field theory describes particles as excitations of underlying quantum fields. In this framework, entanglement takes on an even more fundamental character. It turns out that even the empty vacuum of space is full of entanglement. The quantum field in one region of space is entangled with the quantum field in neighboring regions. This vacuum entanglement is a permanent, intrinsic feature of the universe. It cannot be switched off or eliminated. And yet, this pervasive vacuum entanglement does not allow communication. If it did, everyone would be communicating instantly with everyone else, all the time, because the vacuum entanglement is everywhere. The no communication theorem applies just as strongly to vacuum entanglement as to the entanglement between individual particles. The correlations are there, woven into the fabric of empty space, but they carry no information. This perspective makes the no communication theorem seem even more natural. If entanglement is simply a feature of the quantum fields that make up reality, rather than some special connection created between specific particles, then of course it cannot send information. It is not a communication channel. It is a property of the fields themselves. Asking why entanglement cannot send information is a bit like asking why the smoothness of spacetime cannot send information. It is a property, not a channel. In quantum field theory, the no communication theorem is actually built into the structure of the theory from the start, in a principle called microcausality. Microcausality states that field operators at space-like separated points commute. In plain language, this means that measurements performed at locations too far apart for light to travel between them cannot influence each other. This is not derived in quantum field theory. It is postulated. It is one of the fundamental axioms on which the entire theory is built. This is significant because quantum field theory is the framework of the standard model of particle physics, which describes every known particle and force except gravity. All of particle physics, all of the experiments at the Large Hadron Collider, all of our understanding of electrons, quarks, photons, and neutrinos is built on a framework that has no signaling as a fundamental axiom. The consistency of this enormous, extraordinarily successful body of physics depends on entanglement not sending information. Now let me discuss something that might seem surprising. There are situations in quantum mechanics that seem to violate the no communication theorem at first glance, but do not actually violate it. These apparent violations are instructive because they show how subtle the theorem can be. One famous example is the quantum eraser experiment. In this experiment, entangled photons are sent through a double-slit apparatus. Normally, when you monitor which slit a photon goes through, the interference pattern disappears. But in the quantum eraser, you can choose, after the fact, whether to observe which path information or to erase it. If you erase it, the interference pattern returns. This seems to suggest that a choice made on one photon can affect what pattern the other photon creates on a screen, potentially faster than light. But careful analysis shows this is not the case. The photon at the screen always produces the same overall pattern, regardless of what is done to its entangled partner. The interference pattern only becomes visible when you select a subset of the photons based on information obtained from the entangled partner. And obtaining that information requires classical communication. The overall statistics never change. Only the sub-ensemble statistics show interference, and selecting the sub-ensemble requires knowing what happened to the other photon, which requires light-speed communication. Another example that confuses people is quantum teleportation itself. As we discussed, teleportation transfers a quantum state from one place to another. It seems like you are sending something faster than light. But the teleportation is not complete until the classical message arrives. Until Bob receives Alice's 2-bit classical message, his particle is in a random state. The quantum state only appears at Bob's end after classical communication. Nothing useful has arrived faster than light. A third example is what is sometimes called quantum pseudo-telepathy. There are certain games that two separated players can win with certainty if they share entanglement, but can only win with some probability classically. Does this mean entanglement is sending information between the players? No. The games are specifically designed so that the players do not need to communicate during the game. They just need correlated random numbers, which entanglement provides. The entanglement helps them coordinate their answers, but neither player learns anything about the other's specific input or actions. In every case, when you carefully analyze what is happening, the no communication theorem holds. The apparent violations dissolve under scrutiny. The theorem is robust, resilient, and precise. It withstands every attempt to circumvent it. Let me now discuss the connection between entanglement and what physicists call monogamy. Entanglement monogamy is a principle stating that entanglement cannot be freely shared. If particle A is maximally entangled with particle B, then it cannot be entangled with particle C at all. Entanglement is exclusive. Jealous, in a sense. This monogamy is another reason why entanglement cannot be used for communication. If you could clone an entangled state, distributing copies to many people, you might find ways to extract information through statistical methods. But monogamy prevents this. Each entangled pair is exclusive. You cannot make copies because that would violate both the no-cloning theorem and the monogamy of entanglement. Monogamy also has implications for the security of quantum key distribution. If Alice and Bob share maximal entanglement, then no eavesdropper can also be entangled with their particles. Any attempt to intercept creates a three-way entanglement that reduces the quality of Alice and Bob's correlation, which they can detect. The security of quantum cryptography is mathematically guaranteed by the monogamy of entanglement. There is something deeply satisfying about how all these principles fit together. The no communication theorem, the no cloning theorem, the monogamy of entanglement, the uncertainty principle, the randomness of measurement outcomes, all of these are interconnected. They form a web of consistency. Pull one out, and the others collapse. They are not separate rules imposed on quantum mechanics from outside. They emerge naturally from the mathematical structure of the theory. They are aspects of a single coherent framework. Let me also touch on something that has generated much interest in recent years, namely the connection between entanglement and black holes. Black holes are regions of spacetime where gravity is so strong that nothing, not even light, can escape. They represent the most extreme conditions in the universe. and they turn out to have a deep connection to entanglement. In 1974, Stephen Hawking showed that black holes are not perfectly black. They emit radiation, now called Hawking radiation, due to quantum effects near the event horizon. This radiation is thermal, meaning it appears random and carries no information about what fell into the black hole. Over time, the black hole slowly evaporates, converting its mass into Hawking radiation until nothing is left. This creates a profound puzzle called the black hole information paradox. If the Hawking radiation carries no information, then when the black hole evaporates completely, all the information about what fell in is lost forever. But quantum mechanics says information can never be destroyed. These two principles contradict each other. Resolving this paradox is one of the most important open problems in theoretical physics. Entanglement is at the heart of the paradox. The Hawking radiation is entangled with the interior of the black hole. As the black hole evaporates, more and more of the radiation becomes entangled with the interior. Eventually, the early radiation should become entangled with the late radiation. But this requires a transfer of entanglement from the interior to the exterior, which raises deep questions about causality and the no-communication theorem. Some proposed resolutions involve the idea that entanglement between the interior and exterior of a black hole is the connection between them. That the interior of a black hole is literally constructed from entanglement, as suggested by the ER=EPRA conjecture we discussed earlier. In this picture, the black hole paradox is resolved by understanding that entanglement, spacetime geometry, and information are all aspects of the same underlying reality. This is cutting-edge physics, still very much under debate. But it illustrates how central entanglement is to our deepest questions about the universe. The no-communication theorem does not diminish the importance of entanglement. If anything, it makes entanglement more mysterious and more fundamental. It suggests that entanglement is not a tool for communication, but something even more basic. Something related to the very structure of space-time and reality itself. Now let me turn to discussing the future of entanglement research. Where is this field heading? What might we learn in the coming decades? One major direction is the scaling up of quantum entanglement. Currently, we can entangle small numbers of particles, from individual photons and atoms up to systems of about 100 quantum bits in quantum computers. The next frontier is entangling larger and larger systems. Can we entangle molecules, viruses, living cells? In 2019, researchers entangled a mechanical oscillator containing trillions of atoms, showing that quantum mechanics operates even at these scales. The question of where, if anywhere, quantum mechanics breaks down as systems get larger remains open. Another direction is the development of quantum networks. Multiple research groups worldwide are working to connect quantum devices over long distances using entanglement. The goal is a quantum internet that uses entanglement as a resource for distributed computing, secure communication, and precise synchronization. Several cities, including Hefei, Shanghai, and Vienna, already have rudimentary quantum network links. The goal for the next decade is to extend these to national and eventually global scales. The intersection of quantum information and gravity remains one of the most exciting frontiers. Understanding how entanglement relates to spacetime geometry, how the no-communication theorem connects to the causal structure of general relativity, and whether entanglement can help us understand quantum gravity, these are questions that could lead to revolutionary insights about the nature of reality. There is also growing interest in using entanglement to test fundamental physics in new ways. For example, researchers are exploring whether gravity can entangle two particles. If it can, this would prove that gravity is quantum in nature, resolving one of the great open questions in physics. Experiments to test this are being designed, and results might be available within the next decade. The field of quantum error correction, which uses entanglement to protect quantum information from noise, is advancing rapidly. Understanding how to maintain entanglement in the presence of environmental disturbance is crucial for building practical quantum computers. The techniques developed here also shed light on fundamental questions about how information behaves in quantum systems. All of these research directions respect the no communication theorem. None of them attempt to send information through entanglement. Instead, they use entanglement as a resource within the constraints that quantum mechanics imposes. They represent a mature understanding of what entanglement is, what it can do, and what it cannot do. The no communication theorem is not an obstacle to progress. It is a guide that tells us where to look for useful applications of this extraordinary phenomenon. Let me now address a question that I think deserves careful attention. Why do so many people find it difficult to accept that entanglement cannot send information? Why does this limitation feel wrong to so many people, even after they understand the physics? I think there are several reasons. First, human intuition is built for the classical world. We evolved in an environment where correlations between distant things always have explanations in terms of signals or common causes. When we hear that two particles are correlated but no signal passes between them, our brain immediately wants to invent a signal. It feels incomplete without one. This is not a failure of intelligence. It is a mismatch between our evolved intuitions and the actual structure of reality at the quantum level. Second, the language we use to describe entanglement is misleading. We say one particle knows what the other is doing. We say measurement on one causes the other to change. We say there is a connection between them. All of these words carry implications of communication and signaling that are simply not present in the physics. But once the words are in your head, the intuition of communication is hard to shake. Third, science fiction and popular culture have overwhelmingly portrayed entanglement as a communication method. From novels to movies to television shows. The Ansible or quantum communicator is a standard science fiction device supposedly based on entanglement. This cultural saturation creates expectations that are hard to overcome even when the physics is clearly explained. Fourth, there is something psychologically unsatisfying about a connection that cannot be used. It feels like a waste, like nature is teasing us, showing us something incredible and then snatching it away. This emotional response is understandable but says nothing about the physics. Nature is under no obligation to satisfy our preferences. The truth is that accepting the no communication theorem requires a genuine expansion of one's conceptual framework. You need to accept that correlation and communication are different things. That connections and signals are different things. That two events can be related without one causing the other. These are genuinely new conceptual categories that do not exist in everyday experience. Learning to think in these categories is part of understanding quantum mechanics at a deep level. Let me now bring us toward the conclusion of this exploration by discussing what I think is the deepest insight we can draw from all of this. Quantum entanglement shows us that reality has a relational structure that goes deeper than space. Two particles, separated by any distance, can be as intimately connected as if they occupied the same point. But this connection is not a channel for communication. It is something else entirely. It is a shared identity, a common state. A single quantum system that happens to have two parts in different locations. When Alice measures her particle, she is not sending a signal to Bob's particle. She is interacting with one part of a single, undivided quantum system. The system responds as a whole, not through signaling between parts. There is no between, no gap for a signal to cross. The system is already one thing. Space, in a sense, is irrelevant to the quantum state. The particles are entangled not because something connects them across space, but because they share a state that is not spatial in nature. From this perspective, asking why entanglement cannot send information is like asking why your left hand cannot send a message to your right hand. They are parts of the same body. There is no need for communication because there is no separation at the fundamental level. The appearance of separation, the appearance of two distinct particles in different places, is something that emerges at a higher level of description. At the quantum level, the entangled system is one. But this unity does not allow communication, because communication requires differentiation. It requires a sender and a receiver, a before and after, a choice and a response. The very oneness of the entangled system is what prevents communication through it. Communication requires separation, and entanglement is, at its core, the absence of separation. This is perhaps the most poetic way to understand the no communication theorem. It is not a limitation imposed on entanglement. It is a consequence of what entanglement is. Entanglement means two things are actually one thing, and one thing cannot send a message to itself. Communication requires two separate entities. Entanglement means the entities are not separate. The inability to communicate is not despite the connection, but because of it. Now, I want to be careful here. This is a conceptual way of understanding the physics, not a literal physical claim. The mathematical theorem stands on its own, independent of any interpretive framework. But this way of thinking helps explain why the universe is structured the way it is. Why there is this beautiful, tantalizing, untouchable connection that refuses to carry messages. Let me also reflect on what this tells us about the nature of space itself. If entangled particles are fundamentally one system, regardless of their spatial separation, what does this say about space? Perhaps space is not as fundamental as we think. Perhaps spatial separation is an emergent property, arising from our coarse-grained description of reality, while the fundamental level knows nothing of distance. This connects to the ideas from the ER equals EPRA conjecture and the emergence of spacetime from entanglement that we discussed earlier. If these ideas are correct, then space itself is a consequence of patterns of entanglement. The question why can entanglement not send information across space becomes almost self-referential. Space is made of entanglement. Asking why entanglement cannot communicate across space is asking why the threads of the fabric cannot send messages across the fabric. The threads, the fabric, they do not traverse it. These are speculative ideas at the frontier of theoretical physics. They are not established facts. But they represent the direction in which our deepest thinking about quantum mechanics, gravity and reality is heading. And they give us a sense of how profound the implications of the no communication theorem might ultimately be. Let me now discuss one more experimental aspect that I find particularly illuminating. In recent years, physicists have performed what are called delayed choice experiments, which test the no communication theorem in particularly striking ways. In a delayed choice experiment, the decision about what measurement to perform on one particle is made after the other particle has already been detected. For example, Alice's photon arrives at a detector and is measured. Then, microseconds later, the decision is made about what to do with Bob's photon. According to quantum mechanics, the correlations still hold. The results still match, even though the influence, if any, would have to travel backward in time. This might seem to prove that entanglement really does involve faster than light, or even backward in time communication. But it does not. Once again, the correlations are only visible after comparing results. Neither Alice nor Bob, looking at their own data alone, can see any effect of the other's measurement. The delayed choice aspect is irrelevant to what either observer experiences individually. It only matters for the joint statistics, which require classical comparison. Delayed choice experiments are particularly powerful demonstrations of the no-communication theorem because they eliminate any possibility of subliminal signaling. If the choice is made after the other particle is already detected, no signal of any speed could have carried information in the usual way. And yet the correlations persist, and yet no information is transmitted. This confirms that the correlations are not mediated by any signal at all, faster than light or otherwise. They are simply a feature of the quantum state, existing outside the framework of signals and communication entirely. Now let me bring up the concept of quantum discord, which is related to entanglement but distinct from it. Quantum discord is a measure of quantum correlations that exists even in some states that are not entangled. It shows that quantum correlations are richer and more diverse than entanglement alone. Even discord, however, cannot be used for communication. The no-communication theorem applies to all quantum correlations, not just entanglement. No quantum phenomenon whatsoever allows faster than light signaling. This universality is important. It tells us that the no-communication principle is not specific to entanglement. It is a general feature of quantum mechanics. Every quantum phenomenon, every quantum state, every quantum operation obeys it. It is woven into the fabric of quantum theory at the deepest level. There is no quantum loophole, no exotic state, no clever manipulation that can circumvent it. Let me also mention the role of complementarity in the no-communication theorem. Complementarity, first articulated by Niels Bohr, states that quantum systems have complementary properties that cannot be simultaneously measured with precision. Position and momentum are complementary. So are the spins in different directions. This complementarity is deeply connected to the impossibility of communication through entanglement. If Alice could simultaneously determine both the spin of her particle A and D, influence Bob's particle in a controllable way, she might be able to send information. But complementarity prevents this. The properties that are correlated in entanglement are precisely the properties that are subject to complementarity. You cannot gain full information about both complementary properties at once. This limitation, combined with the randomness of individual measurements, ensures that no communication is possible. Complementarity, randomness, no cloning, monogamy, no communication. All of these principles support and reinforce each other. They form a consistent, interlocking set of constraints that together define what is possible in the quantum world. Remove any one of them, and the others fall. They are not separate rules, but aspects of a single coherent structure. I want to share one more thought experiment that I think beautifully illustrates why entanglement cannot send information, and why the correlations are fundamentally different from communication. Imagine you and a friend are about to be separated. Before parting, you flip a coin and each look at it. It is heads. Now you travel to opposite sides of the galaxy. You know your friend saw heads. Your friend knows you saw heads. This knowledge connects you across the distance, but obviously no information was transmitted at the moment you used that knowledge. The correlation was established when you were together, and you each carry your half of the knowledge. Now imagine the quantum version. You share an entangled pair. You have not measured yet. You fly to opposite sides of the galaxy. Now you measure. You get up. Instantly, you know your friend will get down. Is this the same as the coin scenario? It seems similar, but Bell's theorem tells us it is fundamentally different. The outcomes were not determined before measurement. There was no pre-existing fact that you would get up and your friend would get down. That fact came into existence at the moment you measured. Yet no signal was sent. This is the heart of the mystery. The outcomes are not predetermined, yet they are correlated. No signal passes, yet they match. It is as if the universe itself enforces the correlation at the moment of measurement, without any mechanism, without any channel, without any signal. Just the bare fact of correlation emerging from the mathematical structure of the quantum state. And yet, you cannot use this to communicate. Because the outcome you got, whether up or down, was random. You could not choose it. You could not encode a message into it. Your friend, measuring their particle, sees a random result. They have no way to know whether you measured before them, after them, or at the same time. They have no way to know what direction you measured in. They have no way to distinguish. The universe just correlated our results from my result, was random and independent of everything. This is the resolution. The universe enforces perfect correlation while simultaneously ensuring that neither party can detect or use that correlation without classical communication. It is as if nature says, yes, I will connect these particles across the cosmos. Yes, their fates will be linked. But no, you may not whisper secrets through this link. The link is mine, not yours. You may use it for computing. You may use it for security. You may use it to test the foundations of reality. But you may not use it for messages. Let me now discuss how this understanding of entanglement and the no-communication theorem influences practical quantum technology development. Engineers building quantum computers need to create and maintain entanglement between many quantum bits simultaneously. The no-communication theorem means they do not need to worry about quantum bits in one part of the computer accidentally sending spurious signals to other parts. The entanglement connects them computationally, but does not create unwanted communication channels. This is actually very convenient for quantum computer design. For quantum network designers, the no-communication theorem means they need to plan for classical communication channels alongside their quantum channels. You cannot build a quantum network that operates solely on entanglement. You need both quantum and classical links. This influences the architecture of quantum networks, the protocols used for quantum key distribution, and the design of quantum repeaters that extend quantum links over long distances. For quantum cryptography, the no-communication theorem is actually the basis of security. If entanglement could send information, an eavesdropper might be able to extract key information from entangled particles without disturbing them. But because entanglement cannot send information, any interaction with entangled particles inevitably disturbs them, making eavesdropping detectable. The very limitation that prevents communication is what guarantees security. This dual nature of the no-communication theorem, being simultaneously a limitation and a resource, is one of its most elegant features. It constrains what we can do in some ways while enabling things in other ways. Quantum technology does not fight against the no-communication theorem. It works with it. It exploits both the existence of entanglement and the impossibility of signaling through it. Let me share a thought about what this tells us about the nature of physical law. The laws of physics are often presented as constraints, as restrictions on what is possible. Gravity prevents you from floating away. Thermodynamics prevents perpetual motion. The speed of light prevents instant communication. These sound like limitations, like the universe saying no. But each of these constraints also enables something. Gravity enables orbits, which enables stable solar systems, which enable life. Thermodynamics enables engines and computation. The speed of light enables causality, which enables coherent experience and meaning. Similarly, the no-communication theorem enables quantum computation, quantum cryptography, and quantum networks. It is a constraint that creates possibilities. This is a deep pattern in physics. Constraints are creative. Limitations are generative. The universe says no in one direction in order to open possibilities in other directions. The no communication theorem is not the universe being stingy with entanglement. It is the universe channeling entanglement toward its proper uses. Uses that are arguably more remarkable than simple communication would have been. After all, we already have communication. We have radio waves, fiber optics, satellites. We can communicate across the globe in milliseconds. We did not need entanglement for that. But we did need entanglement for unbreakable cryptography. We did need it for exponential computing power. We did need it for quantum teleportation. We did need it for precision measurements beyond classical limits. The universe gave us entanglement for the things we actually needed it for, not for the one thing we already had. This might sound teleological, as if the universe has purposes. I do not mean it that way. I am simply noting that the mathematical structure of quantum mechanics is such that entanglement finds its uses in precisely the domains where it provides something genuinely new, something impossible by classical means. This is a consequence of the mathematical structure, not of any cosmic intention. But it is a beautiful consequence, nonetheless. Now let me address one final subtle point before we begin to conclude. Some people, upon learning that entanglement cannot send information, conclude that entanglement is not really non-local. They say, well, if no signal passes, then nothing really happens faster than light, so where is the non-locality? This is a reasonable question, and the answer depends on what you mean by non-local. If non-local means faster than light signaling, then entanglement is not non-local. The no communication theorem explicitly forbids this. But if non-local means correlations that cannot be explained by any local mechanism, then entanglement is non-local. Bell's theorem proves this. The correlations exceed what any local hidden variable theory can produce. They cannot be explained by anything happening at the individual particle locations alone. They require reference to the joint state of both particles. Physicists often distinguish between two types of non-locality. Signal non-locality would mean actual faster than light communication. This does not exist. Correlation non-locality means correlations that violate Bell's inequality and cannot be explained locally. This does exist. Entanglement has correlation non-locality without signal non-locality. This is a precise and consistent position. It is strange, it requires getting used to, but it is well defined and experimentally confirmed. The distinction between these two types of non-locality is crucial for understanding modern physics. The universe is non-local in its correlations, but local in its signaling. Both statements are true simultaneously. They are not in conflict, because correlation and signaling are different concepts. Learning to keep these concepts separate is essential for understanding quantum mechanics correctly. Now let us begin to bring this extraordinary journey to a close. We have covered an enormous amount of ground. We started with a simple image, two coins responding instantly across the universe, and we followed this thread through the foundations of quantum mechanics, the great debates between Einstein and Bohr, the experimental verification of entanglement through Bell's theorem, the mathematical proof of the no communication theorem, the deep reasons why randomness prevents signaling, the philosophical implications for our understanding of reality, the practical applications of entanglement in technology, and the cutting-edge research connecting entanglement to the nature of spacetime itself. Let me summarize what we have learned. Quantum entanglement is a real, experimentally verified phenomenon in which two or more particles share a single quantum state such that measurements on one are instantly correlated with measurements on the other, regardless of distance. These correlations are stronger than anything achievable by classical means, as proven by violations of Bell's inequality. They cannot be explained by pre-existing hidden variables or predetermined outcomes. They represent something genuinely new that quantum mechanics has revealed about reality. Despite these extraordinary correlations, quantum entanglement cannot be used to transmit information faster than light. This is not a technological limitation, but a fundamental law of physics, expressed in the no-communication theorem. The theorem follows from the mathematical structure of quantum mechanics and would require quantum mechanics itself to be wrong in order to be violated. The reason for this limitation is the fundamental randomness of quantum measurement. Neither party can control their measurement outcomes, so neither can encode a message. Both see random results, and the correlations only become visible when results are compared using ordinary, light-speed limited classical communication. This situation is consistent with special relativity because no information travels faster than light. Causality is preserved. The non-locality of entanglement is in correlations, not in signals. These are different things, and distinguishing them is one of the key insights of modern physics. Entanglement, despite being unable to send information, is an extraordinarily useful resource for quantum computing, quantum cryptography, quantum teleportation, and quantum sensing. These applications exploit the strange properties of entanglement within the constraints imposed by the no-communication theorem, finding genuine usefulness in precisely the domains where entanglement provides something impossible by classical means. The deepest implications of entanglement and the no-communication theorem are still being explored. They may connect to the nature of spacetime, the resolution of the black hole information paradox, and the ultimate structure of reality. The no-communication theorem may reflect something profound about the relationship between quantum mechanics and the geometry of the universe. And here is what I find most remarkable about all of this. The universe gave us quantum entanglement, a connection that transcends space, a correlation that ignores distance, a link between particles that is as intimate and immediate as if they occupied the same point. But the universe also set a boundary. It said, "You may observe this connection. You may use it. You may build technologies on it. You may learn about reality through it. But you may not speak through it. You may not send messages across the cosmic link. The connection is for being, not for saying." This boundary is not arbitrary. It emerges from the mathematical structure of quantum mechanics itself. It is related to the randomness of measurement, the impossibility of cloning quantum states, the monogamy of entanglement, and the complementarity of quantum properties. It is connected to the consistency of causality and the structure of spacetime. It is woven into the foundations of physics at the deepest level we can currently probe. The no-communication theorem is not a disappointment. It is a revelation. It tells us that reality is structured in ways that transcend our everyday categories of connection and communication, signal and response, cause and effect. It tells us that the universe has types of relationship that we never imagined possible. Relationships that are real, verifiable, and useful, but that do not fit into any box that classical physics provides. Every year, our understanding of entanglement deepens. Every year, new experiments test its limits, new applications exploit its properties, and new theoretical insights connect it to ever more fundamental aspects of reality. The no-communication theorem stands firm through all of this progress, as solid and reliable as the day it was first proven. It is one of the fixed points of our understanding, a landmark by which we navigate the strange landscape of quantum reality. And perhaps this is the ultimate lesson. The universe is stranger than we can intuitively grasp. It has connections we never imagined. It has relationships we have no words for. It has structures that exceed our everyday concepts. But it is also coherent, consistent, mathematically precise. Its strangeness is not chaos. It is order of a kind we are only beginning to comprehend. Quantum entanglement refuses to send information because it is something deeper than a communication channel. It is a feature of reality itself, a thread in the fabric of the universe, a relationship so fundamental that it may underlie space and time themselves. Asking it to carry our messages is like asking the laws of physics to deliver our mail. It is a category error. Entanglement is not for communication. It is for being, for existing, for connecting reality to itself across the unfathomable distances of the cosmos. And that, I think, is one of the most beautiful things physics has ever taught us. The universe is connected in ways that transcend space. But this connection is not a tool for our use. It is a truth about reality. A quiet, profound, mathematically precise truth that does not shout, does not signal, does not communicate. It simply is. And in being, it makes possible a universe where space exists, where time flows, where particles dance, where stars form, where life evolves, where consciousness emerges, and where beings like us can sit and marvel at the extraordinary structure of the reality we inhabit. If this video has changed how you think about reality, I want you to share it with someone who loves science, someone who has looked up at the stars and wondered what holds the universe together. Send them this video and let them experience the same journey you just did. And subscribe to this channel if you want more deep explorations like this one. We go to the foundations, we explore the mysteries. We take the time to really understand not just the what, but the why. Leave a comment below telling me what strikes you most about the no communication theorem. Is it the randomness? Is it the connection to causality? Is it the fact that every interpretation agrees? Is it the idea that entanglement might be deeper than space itself? I want to know what resonates with you. I read every comment, and your thoughts fuel future explorations. Until next time, keep questioning. Keep wondering. Keep looking at the universe with fresh eyes and an open mind. Because the more we learn about reality, the more we discover that it is stranger, more beautiful, and more profound than anything we could have imagined. The universe is not done surprising us, and we are not done exploring it. The quantum world whispers its secrets to those who listen carefully, who set aside their assumptions, who accept what the mathematics reveals even when it confounds intuition. Today we listened. Today we learned that the universe has connections that transcend distance, but guards them with randomness that transcends our control. We learned that reality is both more connected and more private than we ever suspected. And we learned that the deepest truths about the universe often come not from what it allows, but from what it forbids. Quantum entanglement refuses to send information. And in that refusal, it teaches us more about the nature of reality than any message ever could.